F block elements or the inner transition elements, and initially we are dealing with the lanthanoids. These elements, they are called inner transition elements because here the filling of electrons is occurring in f orbitals, which is n minus 2 f orbitals. So they are known as inner transition elements. The general configurations are n minus 2 f 0 to 14, n minus 1 d 0 to 1, and ms 2. The 4f transition series, inner transition series, they are known as lanthanoids, and the 5f inner transition series, they are known as actinoids. They are called lanthanoids because they follow immediately after lanthanum, and they follow immediately after actinium, so they are known as actinoids. Now we are talking about electronic configuration of lanthanoids. Here you can see the 6s orbital is full in all of the elements, and filling is taking place in 4f orbitals. Now talking about sizes and one important concept, lanthanoid contraction. You have named it earlier in the previous chapter also, in the transition elements also. So lanthanoids, as we move across the lanthanoids, the size decreases. It is due to the ineffective shielding of the 4f electrons. The 4f electrons, they have imperfect shielding, so they cannot shield the charge effectively. So the size gradually decreases. So, and this effect or this phenomena is known as lanthanoid contraction. Consequences of lanthanoid contraction. Because of lanthanoid contraction, 4D and 5D transition series, they closely resemble each other. The IE of 5D transition series are higher than those of 3D and 4D, and because of lanthanoid contraction, it is very difficult to separate lanthanoids. Now we'll further move on directly to the oxidation states of lanthanoids. In lanthanoids, +3 oxidation state is very stable, and the stability of +3 oxidation state is mainly due to empty, half-filled or completely filled F subshells. So we can say 4F0, 4F7 and 4F14 configurations are most stable. So in CE4 positive, 4F0 state is there, so it is stable. In PB4 positive, 4F7 state is there, so it becomes stable. +2 and +4 oxidation states are also shown by these elements. The irregularities are due to, again I have told, because of empty, half-filled or fully filled F orbitals. Because +3 state is stable, so the +2 oxidation state, they tend to change to +3 by losing electron, so they act as reducing agents, and +4 they tend to change to +2 by gaining electron, so they act as good oxidizing agents in aqueous solutions. Now talking about properties, chemical properties has been deleted, but we'll talk about physical properties. They are silvery white soft metals, they tarnish in air, they are good conductor of heat and electricity. Some of them, like promethium, they are radioactive. And one thing is also asked about the use. One alloy of lanthanoids, which is called mish metal, it contains 95% of lanthanoid and 5% of iron. It is used in bullet shells. So about mish metal, it is asked in examinations. Chemical properties have been deleted, so we'll straight away move on to actinoids. In actinoids also we have to just study about the actinoid contraction only. The rest has been deleted. So in actinoids, most of the elements, they are radioactive in nature, so it is very difficult to study the reactions of actinoids also. Actinoid contraction, again like lanthanoid contraction, actinoid contraction is also the decrease in size when we move across actinoids. But one thing is asked, that why actinoid contraction is greater than lanthanoid contraction. So the answer is that the 5F, the poor shielding effect of 5F electron is more than the poor shielding effect of 4F electron. Therefore, actinoid contraction is always greater than lanthanoid contraction. So that's all, children. In this video, we will continue with the rest in next video.